Yesterday, we noticed three properties, two of which are obvious, the third one not so much. The third one's in a lot of ways the most important of the three. It comes up a lot. It's really useful. Okay, but we noticed three properties, and they were just like demonstrations of the properties kind of thing. But now we're going to do a formal proof. Okay, and these are definitely, you need to know all of them, and you'll see why they do come up. The product law of logarithms comes up quite a bit as well, but it's the power law that we use a lot. But anyway, they all do come up. So we're going to start for each of these three. We start with this. We start with doesn't look good. X is, this is just, we're defining x to be the log base a of m. Okay, so that's our statement. And we're defining y to be log base a of n. And it's useful to rearrange each of these and rewrite them in exponential notation, right? So that means that m equals a to the x. And n equals a to the y. So the base stays the same. And that's how you rewrite them. Pretty good? We haven't done anything yet. That we start with that. We didn't figure that out or anything. So for the product law of logarithms, what we're going to start with is, what is m times n? And in fact, if you start with the correct definitions for x and y and m and n, and then you start with m times n, the rest of this comes together fairly easily, I would say. So we just replace this with a, this is important because this is that. Right? It's the m times n. Okay? So we start with, this is a to the x times a to the y. How can I rewrite this? Jason? Very good. See, that's just a guess. Jason doesn't know what's happening, but like that's all you can do. And probably a lot of you would have known, but I don't know if that's what we're supposed to do, because this is a proof. Only certain people are allowed to do proofs, not me. That's how people think, right? What else could you do? So yeah, of course, let's try that. Okay, and what could we do now? Well, this one's a little bit, I mean, it's maybe not obvious, but we're going to take the log of both sides. Okay, so this is log to base a. Okay, so this becomes log base a of the whole left side, m times n, equals, log base a of a to the exponent x plus y. So that whole exponent. Yeah. So now what? Does anybody notice what we can do now? Using one of the properties from yesterday. Yeah?
The right side will just be x plus y.
Very good. So log base a of m times n, that whole thing, equals x plus y. And that's a property from yesterday. Log base a of a to some exponent is the same as the exponent, right? If you're not sure of that step, you got to go back and check the properties from yesterday. And remember I said, like, a lot of these properties are important. They come up a lot. Okay, but we used a property that we know that we sort of demonstrated yesterday. We didn't do a formal proof yesterday, but basically did. And what is x and what is y? So I just have to look back up here. Oh, that means log base a of m times n equals x, which is log base a of m, plus y, which is log base a of n. Well, that's what we were trying. That's it. That's the property from yesterday. Okay. So there's our formal formula and proven for all values of x, m, n, y, a. Well, not quite all values of a because a can't be negative, but anyway. Yesterday we noticed that there was like a connection there, but it could have been a fluke. Although if you look at it carefully, you can see why it works out that way, but there's your proof. Everybody okay? Everybody get that? So the quotient goes very similarly. We're going to start with, m divided by n. So why don't you go ahead and sort of try the first few steps on your own and see what happens. I can't give you too much time because I don't want to spend a ton of time on this, but see if you can. It's literally the same steps, just with dividing and the things that go with dividing. What was the first step we did for the last one? We just replaced m and n with what they equal from above. So a to the x divided by a to the y. See if you can beat me to the next step. You can beat me down the page. Some people hesitated. You didn't even want to start that first step. You got to build some confidence. You got to try some things. And literally, we're following, say, like, what did we do in the last one? Oh, we noticed that then you can add the exponents. But what do I do when I divide? Subtract the exponents. So it's a to the x minus y. And then what do we do in the last one? We took the log of both sides, log base a, that's important. And I'm just going to write it this way, m over n, but it doesn't matter if you wrote it the other way. Log base a of a to the x minus y. So that means log base a of m over n equals x minus y. But what are x and y? Nice. Log base a of m minus log, base a of n. And that's the property. That's property formula, whatever you want to call it. Quotient law or quotient property of logarithms. Okay. Any questions about either of those? Yes. Probably not on this quiz, but you never know. I'll tell you in advance if you have to memorize them. This one is a little bit, it's actually, I mean, it's just as simple in some ways, like there's not very many steps. It's fairly straightforward, but it's maybe not quite as obvious what the steps are. But anyway, m, remember this is just a reminder because it's way up my page, but this is from before. M by definition is a to the x, right? That was the relationship we gave it. So I'm going to take that and I'm going to plug it in to log base a of m to the n. That means log base a of a to the x all to the n. And you don't have to do this, but this is the whole argument of the log, right? So if I just look at the argument of the log, a to the x to the n, how can I rewrite that part just to simplify matters for now? Yeah. Not plus. Good. Yeah, times. Very good. Log base a of a to the x times n. So that's just exponent properties, right? Power of a power, we multiply the exponents. And now what do I notice? The same property that we're using before, log base a of a to some exponent equals that exponent. So this just equals x times n. Yes? That's okay? Now, this next step is quite tricky. You follow what I'm doing here? Is everybody okay with that one? That's a joke. It's just gonna simplify things. To change them around. So x times n is n times x, the same thing. And then remember, what does x equal? From before, log base a of m. So this equals n times log base a of m. And all of this came from that top line. It was just equals, equals, equals all the way down. So this is log base a of m to the exponent n. And look, there you have it. That's the property that we wanted. Log, this is different from the other ones we were using because the base of the log and the base of the power in the argument of the log are not the same, right? Log base a, it's not a to the n. It's m to the n. So they're all different. But what it tells us is if in the argument of the log, I have an exponent, I can take that exponent out front and multiply. Man, it is useful. John?
Why would we change the n to a?
It's kind of confusing that we used n in this case because it is part of the thing, but it's like kind of unrelated. Maybe I should change that variable for a future year because it's not the same n, or it's just not useful. We don't need to in this case. That's all. Yeah. So we use n just because, I don't know, it's one of the ones we tend to use, but it turns out we don't need to worry about its definition in terms of the other things. Okay, so there you go. So there's our three proofs. They're nice, simple proofs. They're kind of eloquent in a lot of ways. There's only a few steps to them, but you got to know what to start with. Like you got to know what to let x equal and to rearrange it, and let y equal and to rearrange it. And then from there, they kind of just work. So that's it for the properties. The sort of 4, or maybe was it 5 that we looked at yesterday. I remember there was that one that's a little bit different that people always forget about. So don't forget about that one. And then the other ones that we use a lot. Okay, so all of those, these 3, those are the properties of logarithms you need to know. Up to this point in this unit, you have got to be getting very familiar with log notation and how to rewrite it as exponential notation and what a logarithm means. Like you really should be coming to terms with that at this point. I said in the beginning it was like translating to a new language, but now you should be starting to get a lot better and starting to maybe see logarithms for what they are in and of themselves. Okay, so you really want to get that. And we've done evaluating logs and rewriting in exponential notation. And now we've looked at a bunch of properties. And so there's a few different types of questions working with properties of logs today, but then we get into solving all different kinds of equations. And really by the end of today, we've done all of the solving exponential equations using logarithms and just the grade 11 way. And the difference between the two, we saw a little bit of solving exponential equations with logarithms yesterday. There'll be a little bit more of that today, different kinds. And then tomorrow we start solving logarithmic equations, and we'll mix in some of the other kinds of questions as well And then on the quizzes and tests, it's going to be all the different kinds all mixed together. Some you can do with a calculator, some you can't do without a calculator. So this is the kind of question where I notice I don't have actual values. There's two ways that we do this question, sort of forwards and backwards. So we're going to do one forwards, one backwards. I don't know which one is forwards or backwards. It's not, right? But you know what I mean by that. It's got the X's and Y's and Z's and that kind of stuff. Yeah, it's probably really hard to see, right? Is that a Z? Is that a 2? So it's log base A of the fifth root of x cubed y on top and z squared on bottom. Same thing. I shouldn't use Z. I should use something else. I think your worksheet today has W on it, so it's a little bit easier to read because Z is kind of a disaster. Anyway, so here's what this is the kind of question where you probably wouldn't even understand really what it means right in terms of log base A of X, of Y, and of Z. Like, I don't really know what that means. Fair enough, but after today, when you've seen an example, now you should know what it means, okay? And then the opposite, which is our next example, is write as a single log. So you should know what each of those mean. You can also guess at what they mean by what you start with, and you got to recognize this kind of question. Don't get lost. It's just using the properties. The first thing I'm going to do is I'm going to rewrite the exponent of 5, or fifth root of 5 as an exponent. So this is x cubed y over z squared all to the 1/5. And remember, like we saw yesterday, there are different orders that you can do these things in. So I don't know that the order I'm going to do this is the best. It's sort of the one that makes the most sense to me, but I don't know that it's the best. If you think you have the best, then you do it your way, as long as you come to the same end point as me. You may do it in fewer steps. I don't know. So now I'm going to take the 1/5 out front because it's log base A of something to an exponent, and that's the one we just proved, power law of logarithms. I can take that exponent out front. So it's 1/5 times log base A of x cubed y over z. I cross my z's so they don't look like 2's, because otherwise my z's would look like my 2's. So don't be confused about what that little thing is. Now I can split up the argument of the log into separate ones using the other two properties we just looked at. So it's x cubed times y divided by z. You could do this in 2 steps, but I think let's jump to the end point here and let's all do it in one. But if you like, you could think of it as 2 separate steps. If you want to see what that looks like, ask me later. So this is 1/5 times the whole thing of log, it's always base A in this case, of x cubed plus log base A of y minus log base A of z squared. And the 1/5, you got to have brackets around that whole thing, because all I did, it's 1/5 times this, right? And I took this and split it up into that. So it's 1/5 times that whole thing. So watch your brackets there. These are just math class questions. This is not a useful real world skill that we're doing here, but it helps us practice the properties. And there is some just good algebra in here of like, where do the brackets go? That kind of thing, right? And again, order here might depend on the way you see things. So I'll do this in 2 steps. You might even do this part in 1 step. I'm going to take the exponent of 3 in the first one out front. And this is where I have that first part written in terms of log A of x. Because x doesn't have an exponent. It doesn't have any other junk or garbage going on with it. It's just log base A of x. Like, that's your ultimate goal. The next one doesn't have an exponent, so it just stays the same. And the next one, the 2 comes out. And then the last step is I'm going to redistribute the 1/5 back in. So 1/5 times 3 is 3/5. log base a of x plus 1/5 log base a of y minus 2/5 log base a of z. And that's it. That's done. Okay. So if you had done it a different way, you would have avoided taking the 1/5 out front and redistributing it. I don't know if that ends up being extra steps. It might be like one more. I don't know. But again, it just depends on how you see it, what kind of math your brain prefers to do, what's easier on your brain kind of thing while you're working through this. Okay, any questions? That's a type of question you want to be familiar with. It's good practice for the properties, some good algebra in there. So then the other, I'm missing. Oh, is it just here? Oh, no. Oh, I know where it is. It's right there, I bet. Oops. There we go. So this is the other kind. So see how it gives you what we just ended with, and is asking to write as a single log. 2/3 log base a of x plus 1/2 log base a of y minus 1/5 log base a of z. Rewrite that as a single log. Again, you can take as many steps as you want to do this. I would certainly do it at least as a couple. I think in this case we probably only need 2. You might do 3. Everybody okay? Everybody got that written down? 2/3 log base a of x plus 1/2 log base a of y minus 1/5 log base a of z. Okay, so what I'm going to do is I'm going to take the 2/3 from out front and turn it into an exponent. And so just watch for a minute. Put your pencil down and watch. Log base a. This is like of x to the 2/3. Actually, let's just do this. We'll write this down. You could skip this step too, but log base a of y to the 1/2 minus log base a of z. Of z to the 1/5. So this is using that property, the product law of logarithms, or the product property of logarithms, using it in reverse, right? Is everybody okay with that? But ultimately, the 2/3, I want to write it like this. Log base a of the 3rd root of x squared. And that's from grade 11. And we've seen a little bit of that, but I know that that might be something that's not super familiar for people, but that's part of what we're doing is we're reviewing this stuff as we go. Something you certainly need to know how to do. If you're wondering exactly what happened there, well, the denominator of an exponent tells me what level of root I'm taking. So we're rewriting it back in that format. Plus log base a of the square root of y, so you could add the square in there or not. If you want the little 2 in there, you could do it, but we don't need it in this case. Minus log base a of the 5th root of z. So you could skip that first step and go straight to that second one, I think. Or not. It's up to you. And now we can write this as a single log because I have log base a for all of them, and I can use those properties. Again, you might do this in 2 steps. Just add the first 2, like do the product of the first 2, and then divide by the last, or you can do them all at once. So this ends up being log base a of the 3rd root of x squared times the square root of y all over the 5th root of z. Dividing because I was subtracting, multiplying because I was adding. Any questions? A lot of this unit is about what type of question. These ones are a little bit more obvious, but what type of question am I being asked? I know how to do all the different types. I just don't remember which type is which, like which method to use on which type of question. That's because there's so many different kinds of questions in this unit. Everybody good? Everybody good? Okay, let's move on very quickly. You can write this down. There's some discussion about whether or not we even really need to cover this, but I decided why not. Some people like it. And it's a simple formula. It's not one that you need, to be honest with you. You can solve all questions by taking the log of both sides to base 10 and rearranging from there, like some of the ones that we did yesterday and like some of the ones that we're going to do later. But I think in some cases, and some people might like it, or if you have a calculator that you can't change the base, this is how you would do it. This is how you would evaluate a question that wasn't base 10. Okay? So these are just formulas. It's called the change of base formula. And what you want to understand is what it's saying is if you have log of some base, could be any base, but presumably not 10 because your calculator already does 10, or presumably not 10. So log of some base A of B is equal to the log of B divided by the log of A. Not the other way around, although I think it's kind of nice because it's the bigger one over the small one. Like the B is a little bit higher already in the log, in the way we write logs. So the one that's higher goes on top, the one that's lower goes on bottom. So it's kind of an easy way to remember it, right? So it's log of B over log of A. And this bottom one is written with base 10 because there is no base. But you could pick the base. And there's something about that I kind of like where you can pick the base. And in some cases, you can pick a base in a simple way that makes a question really easy, okay? So it could be any base C that you choose, but it's got to be the same on top. You can't choose a different on top than from on bottom. Oh my gosh, no, right? You could pick B on top and A on bottom, and then everything would just be 1 over 1 or whatever. Not 1 over 1, but it would just work out to like trivially. That's not true. It's got to be the same base in both cases. Or it could just be 10. So if you have a calculator that you can't change the base on, this is how you would do it. So let's take a look at a few questions really quickly. We could evaluate most of these without the change of base formula, but we're going to do them with the change of base formula. So get your calculator out. You should already have it out anyway, even though most of the time I've told you not to use your calculator. You want to have it ready because with logs sometimes we do. So what is log base 2 of 64? First of all, what does it equal? Does anybody know? Somebody in here should know. Yeah. Not quite. 6. One more. 5 is 32. 6 is 64. Eventually, if you work with this enough, you memorize them, but that's a good guess. I guess the trick is if you don't have them memorized like reliably, how do you check them? Just multiply it out in your head, which takes a long time, so that's kind of a pain. But anyway, so we're expecting it to be 6. On your calculator, log of 64, make sure you close the bracket if you have to, divided by log of 2 equals, oh my gosh, 6. Log of 64 over log of 2, and that gave me 6. And those were log base 10. Because that button on my calculator always does base 10. That's something you should not take for granted. You should know that's what it's doing. But that's the whole point of this change of base formula is if your calculator doesn't change base for you, this is how you do it. Log base 6 of 1 should be what? 0. So this is going to be log of 1 over log of 6. 0. Okay, you try the rest. Round to 4 decimal places if necessary, it says. Calculator questions now, be great to ask them. Now here's the last trick though. So if you're not allowed to use your calculator, this is not important because you won't be able to use your calculator. So you have to do everything with properties. What if it's the final test where you will have your calculator, but you just have to show your work? Because this question, I can, if I rewrite in exponential form, which doesn't make any sense, it's not equal to x, but anyway, I can get it. I could get like an exact value of it. Same with this one. So there are some that aren't obvious like this necessarily what the answer is, because I can't rewrite 32 as a power of 4. I can't do that, but I can write them both as powers of 2. So like there is a way that you can find the exact value of this. But if I punch it in my calculator, I mean in this case, you probably get an easy one. Most of you, your calculator probably gives you the fraction answer. I actually switched my calculator to give me the decimal answer just because that's usually what I want if I'm using my calculator is the decimal answer. So this one gave me 2.5, which is 5 over 2. And I mean, either of those would be reliable. But on a test, if it was a question that you could find the exact answer of, and you put your calculator in and it gave you a decimal or something like that, like you might have to show your steps. So to some extent, you're going to have to differentiate when you can determine the exact value or not.
For E, do you think that 2?
We're not at E yet. We're just doing it. Just give me a second. So for that one, it's easy. For this one, same thing. I got 1.5, which is 3 over 2. I mean, that's obvious, and either of those answers is fine. But just be aware that these ones I could use properties to find. This one's obviously 2, right? Because 14 divided by 7 is 2? No? 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 You don't think so? What do you think? Okay, good. Yeah, that was obviously... I did that on purpose. But the point is, sometimes our brain plays tricks on us. And we're like, oh, this one's easy. This one's easy. Oh, yeah, this one's easy. It's 2, right? No, oh my gosh, no. You're not just dividing. Think of how silly it is. But the reason is because I see these mistakes being made on tests when you're rushing. And we all know that it's not true. I don't actually have the answer to this one. Divided by log of 7. So yeah, I got 1.3562. Oh, there's a 2 in it. Right, and so be careful that your brain doesn't play those tricks on you. And 14 divided by 7, I can do that, it's 2, right? But that's totally wrong. And then this one is interesting just because it's really close to 4. Doesn't that make sense? Remind us what we're actually doing here. We start using formulas, we forget what we're doing. 3 to what exponent would give me 80? Well, almost 4, really close to 4, just under 4, right? All right, what do we have here? Oh, it's just under 15 minutes. Oh, I think we're good. We only have a couple of examples left. I just want to show you something kind of interesting here. You can write this down or you can just watch. I'm not sure you need it written down. This is kind of interesting. We did a little bit of this earlier in the unit, did a little demonstration of this with exponential functions. What do those functions look like? Log of 100x and 2 plus log of x. So if you think of those as functions like graphs, what's the transformation happening in f? Cassidy, was that a hand up? Oh. Come on, what's the transformation happening in f? We haven't forgot already. We've been doing this all year. Want to take a wild guess? Remember the A, the K, the C, and the D? Like, what's 100? What is it? Is it a vertical stretch? Would a vertical stretch be out here? 100 times log of x? If I told you that, because I think that's the question everybody's wondering. Like, well, we haven't really done transformations of log functions, which is you're right. So if I said vertical stretch would be out front like that, then this must be horizontal, and it's going to be a compression because it has the opposite. Very good. This is a horizontal compression by a factor of 100. That would be really hard to graph, don't you think? Have you ever done a horizontal compression by a factor of 100? Think of the compressions of quadratics. We did like by a factor of 2 and 3, and it got messy. Imagine a compression by a factor of 100. But don't we know something about properties of logs? Okay. Oh, so what's this one? That's just a vertical shift up 2, right? Plus 2. I wrote it at the front, but it's like at the end. So that one would be easy. Vertical shift up 2. Horizontal compression by a factor of 100. But this is log of 100 plus log of x, isn't it? Which is log of 10 squared plus log of x. What's log base 10 of 10 squared? Oh my gosh, same function. You go into graphing software and graph both of those. They're actually the same function. A horizontal compression by a factor of 100 is the same as a vertical shift up 2. That's kind of mind-blowing when you think about the magnitude of those compressions, but that's the logarithmic scale. The logarithmic scale has this strange, just like exponential growth, it has a very interesting relationship with the graphs, and we'll talk about something later in the unit about how logarithms are actually used in the real world. They're huge in certain branches of math, but also other kinds of sciences. And in fact, some of you that are taking this course because you have to, but you actually aren't interested in math or you're trying to get into something else, you might be the ones working with logarithms at some point. Because real world statistics often have logarithms as their scale. But no, don't worry about that now. Okay. Anyway, that was just a side note, kind of interesting little thing after we've done some properties. Here's the last thing that we're doing today, solving some questions. So something you may want to come to terms with in this unit is all the different kinds of equations that we solve. I want to get through all 4 of these examples, so I might go a little bit quick with some of these, so I apologize in advance for that. And there's can be a very big difference between solving exponential equations like this using logs and solving logarithmic equations, which is what we're starting next. So what we start next, and we'll do it for several days, you'll see is quite different. The equations are given as logs, and we do a very specific thing with them. What we've done up till now is solving exponential equations, and sometimes we use logs and sometimes we don't. Sometimes we rewrite both sides in the same base and equate the exponents. But in this case, we're going to use logs. And how do you know when to do what step? Practice. So what I'm going to do is take the log of both sides. This is the log. So I'm going to do base 10, although you could pick a different base, which would change the question a little bit and make it interesting. And if you chose a different base, it would work, but you'd have to use a change base formula eventually, but you could do that. So I'm going to use log base 10 of 3 to the 2x plus 1 equals log base 10 of 99. You have to take the log of the entire left and the entire right So the whole left goes in the argument and the whole right goes in the argument, no matter what it is. Using the power law, I can take the 2x plus 1 out front. And that's the whole point, is I'm trying to get the x out of the exponent. And now I'm going to divide both sides by log of 3. I get 2x plus 1 equals log of 99 over log of 3. And I'm going to subtract 1, and I'm going to divide by 2, just to isolate x. So I'm going to do both those in one step. If you choose to do them separately, that's fine. These end up being, and there's no two ways around it, it's a bit strange, but they end up being big expressions. And punching them into your calculator can take a little while. So go ahead and try that. I'm actually going to skip the calculator part, and I'll put those answers up on the classroom, and you should check them after to make sure that you can do it with the calculator. And if you can't, then let's go over it together. Sometimes you forget to close a bracket if your calculator automatically opens a bracket for a logarithm. But it's just calculator work, so we don't have time for that, unfortunately, right now. So we're going to skip it and move on. And just try a few different ones, getting the rearranging, getting that last one done, and then you can check your answers later. Or if we have time today, you can check them today, but I don't think we will. So same thing, I'm going to take the log of both sides here. Like this one's not different. It just, because it's 7 minus 3x, like the last couple of steps work out a little bit. And those are really grade 9 or grade 10 algebra steps, but in bigger expressions, they come back and haunt us sometimes. So this ends up being 7 minus 3x. I'm putting that in brackets because it's the whole thing times the log of 5 equals the log of 1300. Divide both sides by the log of 5, sorry. So here's where I'm going to subtract 7, and I'm going to do this in 2 steps this time. And this is a little bit weird, but I'm going to just manage. You could do this however you want. You could divide the whole thing by -3, that'd be fine. I'm going to manage the negative because this is a useful trick if you were pursuing math or engineering or science. You know, managing negatives can be very useful. So this is going to be 3x equals, and it's going to flip the sign of each. I multiply the right side by -1. I end up with 7 minus the log of 1300 over the log of 5. Whichever one you think is easier to put in your calculator, do that one. You might think it's easier the other way. That's fine. Again, it's not about like what's the best way in this case. It's really just personal preference. Okay, but now I've got something I can stick in my calculator. What you can't do, folks, is when you get that, evaluate that to a decimal and then start writing the decimal down. Oh my gosh, no. You need to get this step on a test. You need to do everything to there, and then you punch the whole thing into your calculator at once. That's how you would do these questions, okay? Okay, this is the last kind, and you see we've got 2 of these. D is a little bit trickier because it's sort of a mix of both, but this is really the last kind. What do I do when I have 5 or something times like 2 to the x, right? So these ones up here were just 3 to an exponent and maybe 99 to an exponent, or maybe not. This one's 5 times a power. So I'm going to start by taking the log of both sides still. And again, it's the whole thing there. It's the log of that whole thing, whole left and the whole right. And this is where you got to know to do this. Like, I don't know if you would figure it out on your own. You got to practice these enough that you know what to do. This is where I use the product property of the product law. And this ends up being log of 5 plus log of 2 to the x equals log of 4 plus log of 3 to the x. And I'm going to get all the x's on one side and all the other things on the other. So this is going to be log of 2 to the x minus log of 3 to the x equals log of 4 minus log of 5. These are long, messy algebra questions, but it's not crazy hard, but it's long and kind of nasty. And then there's one last step that's tricky that we need to know what to do. I pull the x out front. That's the whole point of what I'm trying to do here, is get the x out of the exponent. Does anybody know what you do in this step? We only have a minute here, so I can't think about it too long, but I'm going to factor that x out of the left side. The thing is, that the first time you see this, it might seem crazy, but all these questions are like identical with number series. These are just your formulaic questions. Step 1, step 2, step 3, step 4, bam. Okay, and you end up with x equals, I divide. You got to get your brackets in the right spot. There's certainly a lot of mistakes you could make. Same thing on your calculator. Moving those numbers around on your calculator, plugging in, having brackets around the whole top, brackets around the whole bottom, plus brackets around the arguments, like it can get messy, but here we are. We're doing it anyway. Messy, not hard, is what I would say. Any questions? There's one more. I'll do it and put it up on the classroom. It's got this and this, but it's the same stuff. You just got to take your time, do your steps a little bit one at a time.